Val d'Arolla in the Valaisan Alps, southwest Switzerland. Less than 5 kilometers away from the border with Italy, 10 kilometers west of the Matterhorn, an area of outstanding alpine scenery. An area which bears the obvious imprint of ice. This is the ice which has contributed so much towards changing the landscape. Glacial ice. Here at the snout of the lower Arolla Glacier, typically the ice is hard and extremely dense, compacted by the intense pressure during movement and by the effects of alternating freeze and thaw. It forms nodules, some of them more than 10 centimeters in length. And as it melts, the coarse crystalline structure is clearly apparent. It's difficult to believe that this ice originated as snow, which fell at high altitude beyond Mont Colomb. The edge of these snowfields, where they overhang the lower valleys, clearly displays the nature of the accumulated snowfalls. They are distinctly banded, the thick white layers marking the heavy winter snowfalls. The narrow, dark bands, the summer melting, and the deposition of dust which penetrates even these high altitudes. Accumulation is greater in hollows, and ice formation is obvious here. Some of the hollows are enlarged to form fully developed cirques. Linked to the upper snowfields by ice curtains, they are fed by drifting winter snow and by the avalanches which frequently break away during the summer. In this isolated cirque overlooking the main valley, a small glacier has formed, 300 meters wide and with an ice wall 50 meters high. A wall which records the change from the recent light banded snow through granular snow, or neve, to glacial ice below. Ice which is at least 5 times as dense as the original snow. Even in a small glacier, there is evidence of intense pressure within the ice, a mass of crevasses on its steeply sloping surface. Here it's about 1 in 5. And near the back wall, the Bergschrund, a zone of multiple crevassing formed by the glacier tearing itself away from the steep rock face. For the ice in this glacier, as in all glaciers, is moving down slope, under the influence of gravity. In the cirque, the pattern of movement is extremely complicated. The entire ice mass rotates, and at the same time it moves down the slope towards the steeper ice fall. Once the ice moves into the ice fall, there is a dramatic change. Now it plunges down a 1 in 2 gradient. The speed of flow increases considerably, and the ice experiences extreme tension. This is extended flow. The ice is stretched, it becomes thin, it cracks, and the icefall becomes a confused jumble of transverse and longitudinal crevasses, grouped to form a complex series of step faults. Crevasses ranging in width from a few centimeters to several meters are also clearly seen near the edge of the glacier, where the frictional effect is greatest and the surface layers are least able to adjust to changing rates of flow. The rapid movement and extended flow which produce the icefall end abruptly when the valley floor is reached. This is marked by a dramatic change in slope, which in turn produces a series of striking pressure bulges, bulges which are the result of a reduction in the rate of flow, from about 1,000 to less than 100 meters per year, the result of a thickening of the ice mass, and of the replacement of the rapid extended flow by slower compressional flow. Below the icefall, the most striking features of the glacier are the ogives. These are alternating bands of light and dark ice, characteristic of glaciers in temperate latitudes. Each pair of bands represents 1 year's flow down the icefall. The clean winter snow forming the white ice, the summer ice, its crystals altered by melting and freezing, its surface contaminated by dust and rock debris, forming the dark ice. The bands of the ogives become closer together towards the snout as compression increases, and they become increasingly curved as a result of the differential rate of flow between the mid-valley ice and the ice near the valley's sides, which is slowed by friction. Evidence of friction and the effects of the sliding of the ice over the rock surface can be seen in areas recently exposed by glacial retreat. Rock surfaces have been grooved and scratched by debris held in the ice, and the valley sides have been smoothed and polished. Because the gradient of the valley floor below the icefall is more gentle and more uniform, the ice is able to adjust to change and movement is more regular. Near the snout, however, the situation begins to change once again. There is a regular pattern of flow, with the major difference lying between the faster-moving surface layers and the basal ice. This regular pattern ends at the snout, as movement virtually ceases because of friction, increased ablation, and the resulting loss of mass, and an inert mass of dead ice may form. The moving ice rides up and over the dead ice, and the flow lines bend towards the surface. Here, the divide between the two types of ice is quite obvious: the cleaner moving ice above, the dirty dead ice below. The ice at the end of the lower Arolla Glacier looks dead, but appearances can be deceptive, for this glacier is now advancing, and this small push moraine bears witness to the advance. Overall, however, melting, or ablation, is the dominant process at the snout. But ablation is not confined to the snout. Its effects can be seen throughout the length of the lower glacier below the icefall. Here, for example, the ice has been protected from melting by a large boulder, and an earlier surface has been preserved. Such ice tables are numerous on most glaciers, but particularly on those with a large amount of dirt on the surface. Nearby, stones which are smaller and so heat up more rapidly in the sun have melted into the ice. In places, the entire surface has been protected from ablation by a very thin cover of debris, a cover which need be little more than a centimetre thick. In this case, an ice cone has been formed, but if the cover is thicker and more continuous, pronounced ridges occur. Ablation is also influenced by the nature of the ice itself. Dirty ice absorbs heat and melts relatively quickly. White ice, however, reflects sunlight. It melts at a slower rate and forms pronounced ridges. The ice surface, which has been made highly impermeable by compaction and repeated freeze and thaw, is awash with meltwater. At the edge of the glaciers, much of this surface water disappears down crevasses or collects in hollows to form deep pools. Towards the center, the surface water forms streams, some of them shallow and temporary, soon obliterated by general surface ablation. Others are perennial, flowing in the same channels for several seasons. Originating high up on the glacier near the icefall, these streams flow very quickly, cascading down the steep ice slope, unimpeded by any irregularities in the channel. Most of the streams only carry a small amount of bedload, derived from the surface layers of the ice, but this is quickly swept away by the moving water, and only the occasional large boulder remains. Streams on glaciers display features which are characteristic of normal streams. On the lower Arolla, for example, there are well-developed meanders. Distinct stream networks also occur. Towards the snout, the network is dense until the water disappears into crevasses, to pass through and under the ice at the glacier's end. This water, swollen by further melting and runoff from the valley sides, emerges as a fully developed pro-glacial stream. Such streams carry large amounts of bedload, released by the melting of the ice. Many are clouded by material carried in suspension. Because water is constantly lost by evaporation from the ice surface, it's difficult to measure total ablation. By measuring the discharge of proglacial streams, where they join, further away from the ice front, it's possible to gain some impression of the water loss from the glacier. At surveyed cross-sections, discharge can be calculated by measuring water depth and velocity at regular intervals across the stream. The channel is divided into at least 3 segments. We measure the stream's velocity using a current meter. This is a small propeller mounted on a large calibrated staff. The current turns the propeller and a reading can be taken. First, it's necessary to establish the stream's depth at each point where measurements are to be taken. The propeller can then be accurately located at a position which represents 40% of the total depth. A depth which experiment has shown gives the average velocity at each point. The meter is then placed in the water for a predetermined time, in this case 10 seconds. The results are displayed on a digital counter. In this case, it's 58 revolutions per 10 seconds. 5.8 revolutions per second. This reading can then be converted using a simple graph. 5.8 revolutions per second represents a velocity of 1.6 meters per second. The discharge at each measuring point can be calculated by multiplying water area and velocity, and the total discharge for the stream can be obtained by adding together the discharges obtained for each segment. These calculations are repeated at regular intervals over a period of time until a wide range of flows has been recorded. Once a minimum of 20 readings have been obtained, they can be plotted and a relationship can be established between discharge and water depth at a fixed location. Thereafter, it's necessary only to measure water depth, and this can be done by using a simple stage recorder. This is simply a piece of tube placed vertically against the bank of the stream. Water is admitted through a fine wire mesh at the bottom of the tube. A rod, calibrated in 5 centimeter intervals, is placed in the tube, and this is used to measure the changing water level. The maximum level, or peak, for each day is indicated by means of sawdust placed in the recorder. This adheres to the rod and is left behind when the water level drops. Here there's been a drop of about 15 centimeters since the previous day's maximum. After each reading, the rod is cleared and fresh sawdust is placed in the tube. Readings taken during a single day show a distinctive curve. Discharge increases during the early morning as the temperature begins to rise, reaching a peak in the early afternoon, before declining more slowly during the late afternoon and early evening. The stage recorder can be used to take daily maxima throughout the melt season, and these readings also show an equally strong seasonal curve with a marked peak in the early summer. But ablation also changes over longer periods of time, and this is one of the factors which can cause the position of the ice front to change. The presence of a stable ice front suggests a state of balance between the rate of snow accumulation within the high snowfield and the rate of ablation on the lower glacier. If there were an increase in the rate of ablation on the lower glacier, discharge in the glacial streams, both on the ice surface and at the snout, would increase, and the ice front would retreat. A reduction in the rate of accumulation on the upper snowfield would also cause the snout to retreat, but the discharge of the outwash streams would not alter markedly. If, on the other hand, snowfall in this area increased, then the annual layers of snow would build up and the volume of ice would increase. Movement down the icefall would become more rapid, and the snout of the glacier would begin to advance, as indeed it would if ablation were to decrease, and in either case it would be many years before such changes would be reflected in the movement of the ice front. The existence of a small push moraine suggests that this has been the trend in the recent years on the lower Arolla Glacier. If so, it would be a temporary reversal of a trend which has seen the glaciers in this area on the retreat during the last 100 years. Such reversals are not uncommon, and the implications can be predicted only if we understand the behavior of glaciers both today and in the recent past.